How cold is it in outer space? Very cold. But to give you some context, you first need to understand heat as scientists do, a measure of how wiggly atoms are. So hot things move quickly, cold things move very slowly. If atoms come to a complete stop, they are at absolute zero. Space is just near to the absolute zero. So you can understand that there is a connection between the temperature and the wiggle. So wiggling is a sort of a movement. So all the movement has a speed. So now you can relate the speed and the temperature. When the molecule vibrates at less speed, it produces less temperature. If the molecule vibrates in a higher speed, then that produces high temperature. Same goes when you increase the temperature of an atom, the atom would vibrate faster. If you decrease the temperature of an atom, the atom would vibrate slowly. Alright, so let's discuss about the absolute temperature. So if you measure temperature relative to absolute zero, the temperature is an absolute temperature. The most widely used absolute temperature scale is the Kelvin, symbolized with a capital K, which uses Celsius scaled degrees. So absolute zero is 0 Kelvin. Another name for the absolute temperature is the thermodynamic temperature. Why? Because the absolute temperature is directly related to thermodynamics. The Kelvin temperature system is named after William Thomson. Lord Kelvin was the first to describe an absolute temperature scale. Alright, let's talk about the Boyle's law. So one of the real life example of the Boyle law is how the human lungs work. Okay, so the lungs are an important organ of the body. They play a vital role in the respiratory system. As the lungs expand, there is a momentary reduction in the pressure. Thus, the pressure inside the body is lower than the outside. Consequently, the surrounding air slips in the body, in the lungs. Okay, this process is called inhalation. So when the lungs relax, the volume of the lungs decreases. Okay, so which increases the pressure momentarily relative to the outside, and the air is exhaled from the body. So this is the perfect example of how Boyle's law works. Robert Boyle explored the relationship between pressure and the volume. He found that the pressure was inversely proportional to the volume, which is to say, as the pressure increased, the volume decreased. Mathematically, he found that the pressure times the volume equaled a constant. We now call this Boyle's law and write it as PV equal to K, where the P is the pressure, V is volume, and K is a constant. If we double the pressure, then we cut the volume in half. The next law is the Charles law. The volume is directly proportional to the temperature. That's what the Charles law means. So in 1787, the French chemist Charles was experimenting on the relationship between the volume and the temperature of a gas. What he found was that if he kept the pressure constant, that the volume of the gas was proportional to the gas temperature. If you double the temperature of a gas, you double its volume. So mathematically, you can write this as volume divided by the temperature as constant. And by the way, to do this, you need to express the temperature in units of Kelvin. Okay, do you know how the hot air balloon works? An air balloon is a classical example of Charles' law. So the working principle of an air balloon is simple. It consists of a bag or an envelope, okay, a basket to carry passengers, and fuel source like propane. So on ignition of the fuel, the air inside the envelope heats up. This hot air expands as per Charles' law. As the temperature of the air increases, the volume of the air also increases, and consequently the density decreases. You have to note that density decreases because the volume increases. D equal to M over V. Okay, so when the volume increases, so the density decreases. Okay, so you can see it for yourself that the number of molecules inside in this balloon is less compared to the molecules outside of this balloon. So this makes the envelope lighter than the atmospheric air surrounding it. So the buoyant force pushes the the lighter envelope up in the air and it flies. So this is how the hot air balloon works. Now let's talk about the pressure law or the Gay-Lussac's law. So here in this law, the pressure is directly proportional to the temperature. Okay, so what Gay-Lussac found was that the pressure of the gas was directly proportional to the temperature. And again, in terms of the formula, he wrote that pressure P divided by the temperature T was a constant. Double the pressure and you double the temperature, and vice versa. And of course, we need to use Kelvin for temperature. So do you know how pressure cooker works? Everybody has pressure cooker at their home. Okay, the pressure cooker is a sealed utensil for cooking food under steam pressure. Okay, so it is usually made up of steel or aluminium. So when heat is supplied, the water inside the cooker vaporizes and the steam is produced. The steam is periodically released through a valve to maintain the operating pressure inside the cooker. If the valve malfunctions and the heat flow is not interrupted, the pressure inside the cooker escalates. The increase in the pressure is due to the Gay-Lussac's law. An example, the pressure of a fixed amount of gas increases with its temperature at constant volume. This high pressure may rupture the cooker and may lead to an unfortunate accident. Avogadro's law. So here the volume is directly proportional to the number of atoms. So it was a few years later in 1811 when Italian chemist Avagadro determined that at constant temperature and pressure, the volume of a gas was proportional to the number of atoms in the container. The idea is the same as the others. Double the number of atoms and you double the volume. This is called Avogadro's law. So when we combine all these four laws, we come up with a combined gas law. So these four laws, Avogadro's law, which connects the number of atoms and volume, Boyle's law, which compares the pressure and the volume, Charles' law, which compares the volume and the temperature, and the Gay-Lussac's law, which compares temperature and pressure, were pieces of what we now call the combined gas law. That means if the pressure or the volume are manipulated, then the temperature or the mole has to be changed as well according to the manipulation. That constant on the right hand side has the name and a symbol. It's denoted R and it is called the ideal gas constant. This allows you to write the relationship between all these variables in what is called the ideal gas law within an equation of PV equal to nRT. So the P, V and T are the pressure, volume and temperature. R is the ideal gas constant. N is the number of gas molecules in volume. Okay, so let's discuss about the kinetic molecular theory. So kinetic molecular theory explains the macroscopic properties of gases and can be used to understand and explain the gas law. Okay, so kinetic molecular theory states that the gas particles are in constant motion and exhibit perfectly elastic collisions. Kinetic molecular theory can be used to explain both, Charles and the Boyle's law. So the average kinetic energy of a collection of gas particles is directly proportional to absolute temperature only. So there are basic assumptions of kinetic molecular theory. So the first one is the volume occupied by the individual particles of a gas is negligible compared to the volume of gas itself. The second one is the particles of an ideal gas exert no attractive forces on each other or on their surroundings. The third one, the gas particles are in constant state of random motion and move in straight lines until they collide with another body. The fourth one, the collision exhibited by the gas particles are completely elastic. When two molecules collide, the total kinetic energy is conserved. And the fifth one is the average kinetic energy of a gas molecules is directly proportional to absolute temperature only. This implies that all molecular motion ceases if the temperature is reduced to absolute zero. Alright, so let's talk about the kinetic molecular theory and the root mean square speed. Okay, so according to the kinetic molecular theory, gaseous particles are in a state of constant random motion. So individual particles move at different speeds, constantly colliding and changing direction. So we use velocity to describe the movement of the gas particles, thereby taking into account of both speed and the direction. Although the velocity of the gaseous particles is constantly changing, particles moving in the opposite directions have velocities of opposite signs. Since a gas particles are in random motion, it is plausible that there will be about as many moving in one direction as in the opposite direction, meaning that the average velocity for a collection of gas particles equals to 0. So as this value is unhelpful, the average of velocities can be determined using an alternative method. So that's why we use the root mean square speed. So it is represented by the equation. M is the molar mass of the gas in kilograms per mole. So KOR is the ideal gas constant and the T is the temperature in Kelvin. Right, so based on this information, you can understand that this absolute temperature is having a positive correlation with this root mean square speed. Okay, so if you want to double up the root mean square speed, then you have to double up the temperature. Simple. But you have to see that in that formula, this temperature is square rooted. It's under the square root. Okay, so if you want to double up this root mean square speed, then you have to quadruple up this absolute temperature because it is under this square root. Okay, so the answer would be the third one.